Isaac Newton's laws of motion, written down in the 17th century, described precisely how particles of any size, from an apple to the moon, behaved. The motion of anything could be predicted. The most intricate machines could be built. They ran as reliably as clockwork, just as Newton imagined the whole universe to work.
Newton's equations tell you exactly what's going to happen in the future. It turned out that the quantum world, the small-scale world, is different from that. It's unpicturable to us, it's cloudy in its character, and it's probabilistic, meaning that we can't say for certain what's going to happen. If this may happen, that may happen. We can say what the chances are, but that's as far as we can go.
The man who first realized the world runs on quantum chance was Werner Heisenberg. In 1927, he proposed the uncertainty principle. It states that because matter is spread out in space, wavy, it's impossible to say exactly where it is and what it might do next simultaneously.
This is absolutely real down in the depths of quantum physics. An electron itself does not know where it is and where it's going.
So we can never be certain about what's happening inside an atom. The effects are so small in our everyday world, we never see them. But the fact that at its heart nature is a game of chance meant scientists had to concede there was a real limit to what they could know with certainty. For many, this was unacceptable.
Several of the quantum pioneers didn't like what they'd invented. Einstein wasn't happy with it, Schrödinger wasn't happy with it, and Einstein hated the idea that the outcomes of experiments could not be completely predictable. And in the famous expression, it's usually quoted, he said that I cannot believe that God plays dice with the universe.
From across Europe, the greatest minds of the age came together to settle the matter of uncertainty. The place was Solvay in Belgium, the year was 1927. The single photograph that remains of the conference shows a unique collection of scientific genius. Max Planck is next to Marie Curie. Behind Einstein are the other great doubters of uncertainty, like Prince Louis de Broglie, the original proposer of the wave theory. And on the top row, Erwin Schrödinger, whose equation made mathematical sense of wavy matter. Schrödinger and the others were not willing to take the leap into uncertainty with the young Turks Pauli and Heisenberg.
They said, we've got to go with the new physics, that's the way the world is, you can't quarrel with that. And there's some quite sharp arguments and discussions between Einstein and Bohr on the one hand, and between people like de Broglie and a very sharp-tongued Swiss physicist Wolfgang Pauli, who essentially told de Broglie, I think, to shut up. He was being stupid. And de Broglie was a sensitive person and didn't like that, and he actually went away and did shut up. So it was a sort of turning point moment in which the young Turks won out over the old guard.
He couldn't believe that the outcome of an experiment depended on chance. And that's what led Einstein, for the last 20 years or more of his life, to fight this more or less lone battle against the theory that was taking physics by storm and try to find flaws in it. And he kept trying to invent experiments, thought experiments, imaginary experiments that would prove that quantum physics couldn't be true. And every time he did, people found ways round his thought experiments and found that they didn't prove that at all. And ultimately, perhaps just as well for him, after he'd died, people actually did some of these experiments for real. And every time they found quantum physics is right, probability rules.
By the late 1930s, quantum theory had found a new home, as European scientists sought sanctuary from Nazi oppression.
So there was this huge shift of science to America. You have this rich country and you have this ability to apply massive technology and money to fundamental problems.
The company that had already made a fortune from knowing the electron was a particle were by now exploring the commercial potential of the wave theory of electrons.
Bell Laboratories began a research program in the 1930s to investigate possible solid-state physics alternatives to the vacuum tube.
Of course, we cannot build a calculating machine as flexible as the human brain. But even a man-made computer, designed to do hundreds of brain-like calculating jobs, might need an Empire State Building to house it and a Niagara Falls to power and cool it, if vacuum tubes were used in its construction.
The goal was to replace the unreliable glass vacuum tubes with tiny solid devices that didn't need a vacuum to work. Scientists already had a good idea of how electrons moved inside a vacuum. They behave like particles.
These aroused monkeys throwing pebbles at a target through a shutter ably portray what goes on in a vacuum tube.
But inside a solid, a crystal, the electrons behave like waves, spreading out and bending around the atoms. To make electrons work in a solid, you need to know about quantum mechanics.
And because electrons are not only particles but also waves, and waves are spread out, then the electron wave sample the overall structure of the crystal, just as the particle-like aspect of electrons carries the unit of electric charge. So in a curious way, the particle-wave duality of electrons is essential. Both aspects of it are essential for understanding how electrons behave in solids, and therefore how electronics works.
In the early 1930s, solid materials were already being used in electrical circuits to detect radio waves. These solids were called semiconductors because they conduct just a little bit of electricity. Using quantum theory, for the first time, scientists could control the flow of electricity with precision. In the 1940s, this led to the development of semiconductor technology as a vital war weapon. Semiconductor radar could detect very small features like the conning tower of a submarine. The transistor was the semiconductor device that could amplify electrical signals, just like the vacuum tube, only better. The tiny transistor was the result of over 10 years' hard work at Bell Labs applying quantum theory to solve a practical problem.
On December 16th of 1947, they succeeded for the first time in amplifying an electrical signal with a solid-state device.
The payoff was enormous.
Through their efforts, you may be able to get music with a flick of your wrist from the so-called Dick Tracy radio.
The miniaturization made possible by semiconductors laid the foundation for a new electronics industry. The first transistor took over 10 years to make. Today, 10,000 times more transistors than the population of the Earth are made every day. They're shrunk down to act as the pumps and valves that drive electrons around microchips. It all depends on quantum mechanics and the strange wave-particle nature of the electron. Over 100 years after its discovery, we can actually see what an electron might look like by using the computer technology it created.
One of the neatest pictures that sums up the quantum world is the one where a ring of atoms has been made as a little fence. You can see the waves of what used to be thought of as quantum particles sort of filling this quantum corral, as it's called. They can't escape. They're stuck inside there, and the waviness is kind of frozen there and can be photographed. That's something that the quantum pioneers would have loved to see.
Don Eigler at IBM has used a quantum microscope to make pictures of atomic surfaces. Each step in this picture of a surface is just one atom high. On top of the atoms, the wavy pattern is caused by a sea of electrons.
These are just electrons which are trapped in the surface layer, but within the surface layer they're free to move around. These electrons are waves, and when a wave bangs into something, it reflects off of it. Well, I'm probably somewhere in error, or maybe I'm just a heretic. I don't believe in this wave-particle duality mumbo-jumbo. I think it's mostly just the leftover baggage of having started off understanding the world in terms of particles, and then being forced because of the quantum revolution to think of the world in terms of waves, and we're stuck with this dualistic way of looking at these very small particles. Don't even think about them as particles. Electrons are waves, and if you think of them in terms of waves, you will always end up with the right answer.